I'm going to talk about the role that the sun has on climate. In a sense, it's we're going to hear more about it, more than what you heard from Professor Ludike in the morning. What I want to talk about, first of all, I'm happy to be here again in the climate conference. It's always a pleasure being amongst friends. What I want to talk about is the following. I want to discuss first what are the problems with the main story that we hear every day. I'm going to mention a few of the arguments that we hear every day and tell you why, I mean, most of you probably know, but I'll emphasize why we should not actually listen to it or why it carries no weight. And then I'll go to a few more scientific arguments why the standard polemic that we hear every day is mostly meaningless at best, or at worst, it's actually, there's evidence that shows that the standard scenario, the standard story that we hear from the alarmists just doesn't hold any water. And one of the main problems that the main standard scenario assumes is that there's nothing else to explain the warming or part of the warming that we've seen over the 20th century. And there is, and that is that the sun has a large effect on climate. So what I will want to do is explain to you what is the evidence that we see that the sun has a large effect on climate, how can we quantify this large effect that the sun has, and then I will leave the actual mechanism, how the sun is affecting the climate, to Professor Svensmark, who will speak immediately after me. But what I will want to discuss is, if we do take the sun into account, how does that affect our understanding of 20th century climate change, and as well as what will happen over the 21st century. Okay, so let us begin with the standard polemic that we hear every day. We have the IPCC that tells us that most of the global warming over the 20th century is anthropogenic, and that climate sensitivity is high, which means that under, say, a business-as-usual scenario, if we burn a lot of fossil fuels, the temperature over the 21st century will necessarily increase by quite a lot. Okay, so what are the arguments that they use in order to solidify their claim? So it turns out that there are several types of arguments. Some of the arguments that we hear mostly in the media, not necessarily by the scientists themselves, are totally irrelevant. And some other arguments, which also the scientists use, are, well, they don't hold any water, to be polite. Okay, so what are the irrelevant arguments that we hear every day? Well, one of the things we hear is the appeal to authority. This is one type of illogical fallacy. The fact that most people think one thing doesn't necessarily imply that they're correct. Science is not a democracy, and even if 100% of the people think one thing, it doesn't mean that they are correct. Moreover, if you actually count how many people really support the idea, you'll find that 97% is just the propaganda number that they came up with to sound as if their story is really supported by most of the scientists, whereas in fact it's much less than 97%. Okay, so science is not a democracy, and anyone who tells you that you should believe global warming is real because most scientists believe it's the case, tell him that's irrelevant. If you want to use arguments, use real arguments. Okay, the second thing that we have to always remember is that when people give us evidence for warming, it's not evidence for warming by humans. If you see polar bears floating on ice somewhere in the Arctic and they tell you, oh, the problem is grave, it could be evidence for warming. And in fact, polar bear population is doing very well. Probably the best that it has been doing over the 20th century. But even if it was evidence for global warming, it doesn't tell you that it's global warming by humans. Okay, so melting glaciers, rising sea levels, or whatever, that's not evidence that it is CO2 which is doing it. And then, of course, there are qualitative arguments. People tell you, oh, the population is approaching 10 billion people. Obviously, we must be doing something to the climate. But who says maybe 10 billion people and the emissions that we have should cause a 10-degree increase, or a 1-degree increase, or maybe a 0.1-degree increase. These kind of qualitative arguments which try to result to your gut feeling bear no weight. I mean, I can tell you, I think that if 10 billion people will spit into the oceans, then the sea level will rise. Okay, that's my gut feeling. Okay, so these are most of the arguments that we hear in the media every day, but they are simply irrelevant. We should, when people argue, they should use real scientific arguments. Okay, so now if you go to the IPCC and you try to distill the evidence that they present us, you really find out that it boils down to two arguments. One is that the warming over the 20th century is unprecedented, and if it's unprecedented, it must be human, or it's unlikely to be natural. And the second argument is that if we try to explain the 20th century with numerical models and we exclude the effects that humans have had on the climate, we find that we cannot explain the warming. And therefore, you must include human effects in order to explain what's going on. Okay, so the first argument is wrong. We know from a few years ago that, the third assessment report of the IPCC had this infamous hockey stick graph star. And we know from a few years later that this hockey stick was simply the hockey stitch. What has been done was, because temperature reconstruction from tree rings showed us that the temperature decreased following 1960, they just cut out the data and they stitched thermometer data, adding two things which certainly don't belong together, getting this ridiculous graph. So we know that 20th century warming is not unique. We know that in the Middle Ages it was as warm as the latter half of the 20th century. Vikings could map the northern shores of Greenland because there was no ice there in summer. So climate has changed over the 20th century and in the past in a similar manner. So this argument just doesn't hold any water. The second argument goes as follows. We can take the radiative forcings that we know we have imposed over the climate. This includes anthropogenic greenhouse gases, the indirect and direct effects of aerosols, the fact that there were large volcanic eruptions which put dust in the stratosphere and blocked some of the sunlight. We can take all these changes in the energy budget, put them into the global circulation models and try to simulate what are we supposed to get. And on the top right, you see a comparison between the measured temperature in black and many realizations of global circulation models, which include the effects of humans, which include the anthropogenic effects. At the bottom, you see the same thing, but when the anthropogenic effects are excluded. Okay, so this is presented by the IPCC. This is in the fourth assessment report, but the same thing appeared also in the fifth assessment report. If you exclude human contribution to the 20th century warming, you cannot explain what has been going on. Hence, we must include, or the effect of humans is large. Okay, this is the second argument. But this too is wrong. Why? Because it assumes implicitly that there is nothing else which can explain the warming. But in fact, there was something which increased over the 20th century, and that is the sun. The sun is a variable star. It changes its outputs, it changes its luminosity, and it changes also its activity, which manifests itself in various forms, whether it be the number of sunspots, the amount of UV, the solar wind, and so forth. So the sun is variable, and as we shall see, it completely overturns the way we see 20th century climate change and other things related to climate, in particular climate sensitivity. Okay, so these are the two main arguments. They are completely irrelevant. They cannot be used to prove that, most of the warming is anthropogenic and that climate sensitivity is large. But before I get into the evidence for the sun, let me first continue with a few more problems that the standard picture has, which will direct us to what the climate really is doing, or what the nature of climate is. Okay, so the first problem is that the size of the warming that we have seen just doesn't fit the predictions. We've seen this graph, I think, yesterday. What we see here are realizations of the temperature increase as predicted by the leading climate models from the 1980s onward, and that's on one hand. On the other hand, you see actual measurements. You see here the satellite measurements. You can also use the surface measurements. This is the Hadley-Kut data. And you see that if you exclude the large effects of El Nino here and in 1997, then basically the global temperature is below what the IPCC models predict. This is called the hiatus, the fact that there is a pause in the warming. They expect the warming to continue, but in fact, it's just evidence that climate is not as sensitive as these models predict. Something is wrong. Another problem is the location of the warming. What we see at the top is the warming as a function of altitude. And in red, it's the warming as a function of altitude as predicted by the climate models. At the bottom, we actually see measurements for what the warming was as a function of altitude as measured with radiosondes, with balloons. And we see that indeed the models fit the temperature increase over the surface, but at higher altitudes, there's something fishy going on. The models predict a temperature increase which is much larger than what you actually observe. So if you had a fingerprint for what the warming should have been from anthropogenic greenhouse gases, it should have given you that there is more warming as a function of altitude, but in fact the observations contradict that. So it means that the nature of the warming is maybe different than what we are being told. Okay, so if there is a fingerprint, it doesn't fit. Another problem that was pointed out by Professor Linzen of MIT is that climate models overpredict the temperature decrease following large volcanic eruptions. Large volcanic eruptions put dust in the stratosphere. It reflects some of the sunlight. We can measure how much of the sunlight is reflected back, and that should cause some warming. But you see that consistently when you have large volcanic eruptions, such as Krakatau, such as Pinatubo, the temperature decrease, this is Krakatau, for example, or Pinatubo. The temperature decrease following the large volcanic eruption is much smaller than predicted by the models. In fact, you can also see it in this graph here, where in 1991 we had Pinatubo erupt. The models give you that the temperature reduction should have been very large, but in fact, the global temperatures decreased by only a little bit. Here at the bottom right, you see the average temperature in the several years before and after large volcanic eruptions, and you see that the temperature, in fact, decreased by something like 0.1 degree plus or minus, something like that, compared to the predictions by the models of 0.3 to 0.5. So obviously, the climate models are too sensitive. They're more sensitive than what the real atmosphere is. So then comes the question, why cannot you predict the climate sensitivity using global circulation models? And the answer is that there are several feedbacks in the system, one of which is extremely hard to predict, and that is cloud cover. And what do I mean by that? Suppose we change the energy budget, we double the amount of CO2 in the atmosphere. The standard value is that we change the energy budget by 3.8 watts per square meter. If we change the energy budget by 3.8 watts per square meter, we should heat the surface by somewhat less than 1.2 degrees. However, if we heat the surface, we will evaporate more water from water vapor from the oceans. And water vapor is an excellent greenhouse gas, so that will want to increase the temperature even more. However, if you have more water vapor in the atmosphere, you'll also have more clouds. And the clouds tend to reflect sunlight and reduce the temperature. They also have a warming effect, but the main effect is that of cooling. And it turns out that nobody knows how to calculate the effect of clouds. Global circulation models basically include recipes for how the cloud cover will change if you change the temperature or the humidity by given amounts. And the climate sensitivity that you obtain from these models is basically almost entirely dependent on those recipes that you choose. So therefore, in computers, you call it GIGO. It's garbage in, garbage out. The recipe that you choose in order to describe the cloud cover is going to give you the sensitivity. This means that you cannot use global circulation models to really predict what the temperature increase is going to be. Here, this is a little bit more technical, just to demonstrate my point. What you see here in the graph is on the right-hand side, you see the climate sensitivity of the model, and at the bottom, you see the feedback that you have through cloud cover. Basically, if you change the temperature by a given amount, by how much do you change the energy budget in the system through the cloud feedback? And you see that the cloud feedback is the main parameter determining what the climate sensitivity of the model is. Namely, this is the dominant source of uncertainty for climate models. Okay, so this also explains why the climate sensitivity quoted by the IPCC hasn't really changed since the first IPCC report, or in fact, since the Charney Committee in 1979. The previous IPCC report, the fourth assessment report, they actually changed it from 1.5 to 4.5 to 2 degrees to 4.5 degree increase per CO2 doubling, because they wanted to rule out the benign scenarios where nothing bad will happen, but the lack of warming over the past 2 decades, the hiatus, forced them to reduce back the lower range to 1.5 degrees. So it's sad that after billions of dollars invested, we don't know what climate sensitivity is any better. Well, we do, it's low, but people don't want to admit it because I don't know why. And well, I know why, but I won't tell you. You can figure it out. Okay, another problem is that there's no fingerprints. You could say CO2, if CO2 has a large effect on climate, you should expect to see some kind of temperature scale over which you have CO2 variations translate into temperature change. And then you would say, aha, just a second, I saw Al Gore's movie, and in his first movie, I actually started seeing the second movie and I fell asleep after 15 minutes. In the first movie, he showed us this graph where you see a temperature reconstruction at the top and a CO2 reconstruction at the bottom, as derived from ice cores in Vostok in Antarctica. And over these 800 million years, you see that there's a very good correlation between CO2 and temperature. And then Al Gore says with his low voice, which I have today because I have a cold, we see that when there's more CO2, the temperature is higher because he wants us to think that larger values of CO2 necessarily cause a higher temperature. What he doesn't tell us is when you have a high enough resolution, you actually find that the CO2 lags behind the temperature by typically a few hundred years. And this is exactly what we heard from Professor Ludeke this morning, and that is that there is an equilibrium between CO2 in the atmosphere and CO2 in the oceans, and it takes several hundred years for this equilibrium to reach, which means that if we change the temperature, we change the equilibrium, and therefore we change the CO2 in the atmosphere. CO2 should have some effects on the temperature, but this graph that Al Gore has shown us doesn't tell anything, doesn't tell us what this relation is. Okay, and in fact, you can go and look over geological timescales. Over geological timescales, you can reconstruct the CO2, which you see at the top, and you can reconstruct the temperature with, in this case, oxygen isotopes in brachiopods or other marine animals. And you see that there is simply no correlation whatsoever between the temperature and the CO2. Do you see any correlation? Well, there was a paper in Science that said there was a correlation, but it's like the emperor's new clothes. This is what I think. Okay, so this lack of correlation can actually be used to place an upper limit of about 1.5 degree increase per CO2 doubling. If climate sensitivity was any larger than that, then you should have been able to see a correlation. But given that there isn't, tough luck, CO2 doesn't have a large effect on climate. Well, it's not tough luck, it's actually good that it doesn't have. Okay, so we've seen that there are a lot of problems with the standard scenario. Let's fix them, let's understand what's going on. And the main thing that we should take into account is the sun. As I told you, the sun is variable, it changes its activity, and this has a large effect on climate, which we should take into account. Okay, so this is, I think, one of the nicest correlation between solar activity and climate that I know of. At the top, you see a proxy for climate, for solar activity. This is carbon-14 measured from tree rings all across Earth. Carbon-14 is formed at the top of the atmosphere by spallation. High-energy particles called cosmic rays hit the atmosphere. These cosmic rays actually come from outside the solar system. But because they're modulated by solar activity, we get less of them when the sun is more active, and therefore we get less carbon-14. So at the top, we have a proxy of solar activity. At the bottom, we have the ratio of oxygen-18 to oxygen-16 in isotopes, in stalagmites, in a cave in Oman, in the southern Arabian Peninsula. And this is a proxy of climates, and in particular, the temperature of the Indian Ocean. What happened is that water with oxygen-18 is heavier than water with oxygen-16, such that the evaporation rates from the oceans are different. But they are also temperature dependent, which means that if the temperature of the Indian Ocean changes, you get systematic variations in those ratios. So at the top, you have a solar proxy. At the bottom, you have a proxy for the temperature of the Indian Ocean. And let me ask you the question again. Do you see any correlation? Yes, thank you. Okay, so you haven't fallen asleep. Okay, it can tell us one of two things. It can tell us that the sun is affecting the climate, or it could be that the climate is affecting the sun. Okay, another example, which we've seen just an hour ago, is the work of Bond. We have ice-rafted debris on icebergs, and then if it's colder, those icebergs can float further south. They melt and they leave it on the ocean floor. So if we dig cores from the ocean floor, we can see whether it was colder or warmer at different epochs, and compare that to solar activity, again, carbon-14 from tree rings, and there is a very nice correlation. Okay, so these graphs tell us that the sun has an effect on climate in the northern Atlantic and in the southern Arabian Peninsula, and there are other such correlations that you can find in other places on Earth, telling you that the sun has large effects at various places on Earth. But in fact, I think one of the most important results is the following. You can not only see that qualitatively there's a large effect that the sun has. You can also quantify the effects that the sun has by looking at the sea level. Plus, we know that the sea level is a global phenomenon. So what we see here in red, we see solar activity. We see solar cycles over almost 100 years. That's the 11-year solar cycle over which the sun changes its polarity. And in black, we see the rates of change of the sea level as derived from tide gauges. And the fact that there is a very strong correlation, again, tells us that the sun has a large effect on climate. However, on short timescales, most of the sea level change is not due to glacial melting, but due to thermal expansion of the oceans. About 70–80% of the signal that you see here is because of thermal expansion. So we can actually use the change in the sea level to quantify the effect that the sun has. We can see how many watts per square meter is the change in the radiative forcing associated with the sun over the solar cycle. And it turns out to be large, about almost an order of magnitude larger than what you would expect from just changes in the solar irradiance. You can also use other data sets. This is, for example, a few years after this work was published, there was a very nice satellite data published from which you can see what the sea level has been doing over the past 2 decades. And if you remove the linear trend, which describes sea level rise from various things, the sea level can be explained, or something like 70 or 80% of the variance in the sea level, or the linearly detrended sea level, can be explained with the sun and El Nino. So again, the sun continues to have a large effect on climate. There are other data sets which you can use in order to quantify the solar radiative forcing. I've shown you the tide gauge records and the satellite altimetry, but there's also cloud cover variations over the 11-year solar cycle, and you can use measurements of, from the Earth Radiation Budget Experiment to see how much are those variations in the cloud cover, or how much do they translate into changes in the energy budget. You can use the change in the temperature of the ocean. It changes by just less than 0.1 degree over the solar cycle in order to quantify the effects of the sun, the radiative forcing effect. Or since 1955, there are also measurements deep into the oceans, or a few hundred meters, and you can use the actual measurements to measure the amount of heat that the oceans have, and from that deduce the changes over the solar cycle. So you see that you can consistently get the same results from 5 independent data sets. So these 5 independent data sets give you that the sun has a large effect on climate, an effect which is much larger than just the change in the total solar irradiance. So that tells us 2 things. One, the sun has a much larger effect, which means that there should be some mechanism which amplifies solar activity. And 2, even if you don't know what this mechanism is, we know that the sun has a large effect on climate, and it must be taken into account. Okay, so if we open the famous graph from the 5th assessment report, which tells us what is the change in the energy budget associated with different components, then we are told that the solar contribution is something minuscule. It's this value. But in fact, given that solar activity increased over the 20th century, and given the relation between solar activity and radiative forcing that we know, that we see from the ocean heat content, we can translate that into the contribution that the sun should have had over the 20th century. And it is this value which the IPCC excludes. Okay? The sun has a large effect. It's comparable to what we humans have been doing, but it's completely ignored. Okay, so a few words about the mechanism itself. Professor Svensmark will actually explain more about it. The mechanism is actually associated with the cosmic rays, which I mentioned before. Not only are the cosmic rays and the spallation and the formation of carbon-14 through spallation by cosmic rays, not only is it a proxy of solar activity, the mechanism itself is associated with the cosmic rays. So again, cosmic rays are high-energy particles coming from the death of massive stars in our galactic vicinity, stars which typically died 10 or 20 million years ago. The solar wind modulates this flux of cosmic rays reaching us. When the sun is more active and the wind is stronger, less of these cosmic rays can reach or can penetrate the inner parts of the solar system and reach Earth. So when the sun is more active, there's a stronger solar wind, less of these cosmic rays reach Earth, and we get less ionization in the atmosphere. And that's because cosmic rays are the dominant source of ions in the atmosphere. And then we know today that these ions play a role not only in the nucleation of small aerosols, but also they increase the survivability of those small aerosols as they grow to become large cloud condensation nuclei. So we'll hear more about it by Professor Svensmark in a second. Just to make you drool a little bit, this is an example of some evidence. When there's a gust in the solar wind, there is a reduction. We can see that in red, the reduction in cosmic rays reaching the Earth. And we can see in different cloud aerosol and cloud parameters that there is a reduction as well. On much longer timescales, we can reconstruct the cosmic ray flux using iron meteorites. So at the top, you see a reconstruction of the cosmic ray flux using iron meteorites over the past 500 million years. And at the bottom, you see the temperature of Earth reconstructed with oxygen-18, as I showed you, that you can do. But it doesn't have any correlation with CO2. It does have a beautiful correlation with the reconstructed cosmic ray flux. OK, so we know that the sun has a large effect on climate. What does it mean? The standard scenario tells us the following. Most of the forcing over the 20th century is due, or change in forcing, is due to human activity. If we now want to explain the temperature rise over the 20th century with this forcing that humans are responsible for, we need a climate which is relatively sensitive. That means that okay, so we need some forcing times a high sensitivity in order to observe or explain the 20th century warming. A high climate sensitivity will in turn predict that a business as usual scenario should give us a large temperature increase over the 21st century. However, as I've shown you, there is a very large neglected contribution to the radiative forcing, and that's the solar contribution, such that the total radiative forcing, or total change in radiative forcing over the 20th century is much larger, perhaps twice as large as what the IPCC use. This means that in order to explain the same temperature increase over the 20th century, we now need a climate sensitivity which is low. And if the climate sensitivity is low, it means that the same emission scenario will now give rise to a low temperature increase over the 21st century. Okay, you can actually model it much better. You can build a model which allows for a free climate sensitivity. You can allow for effects that the sun has. You have to include the fact that the system has a large heat capacity. It takes time for the oceans to warm and cool. When people just correlate temperature with radiative forcing, they're not capturing a very important aspect of the system, which is that the oceans have a large heat capacity. And as a consequence, the climate system acts as a low-pass filter, which means that the response on lower timescales is shorter, and therefore you have to model it more appropriately. So when you do that, you can actually fit the 20th century much better. On the left, we see two graphs. One is the actual temperature measured on Earth, and the other one, and I don't know which one is which because they look almost the same, is the modeled temperature, which we get in a model which allows for the sun to have a large effect on climate. The typical residual that you get this way is about 0.1 degree. On the other hand, on the right, you see the same type of fitting that you can find in the IPCC reports, but in these models, you don't allow for the sun to have a large effect on climate, and when you fit, you find that you can roughly explain, but the residuals are still twice larger. So if you allow for the sun, you get residuals which are much smaller, which means that you can get a much more consistent picture for what has been going on. For those models that fit the 20th century, you can then integrate forward in time with many different realizations. So this is a vanilla-flavored scenario of a business as usual where we don't do anything special. You can integrate it over the 21st century to see by how much is the temperature supposed to increase under various realizations for what the sun will do or what volcanic eruptions will do, and so forth. And then you can compare that to the IPCC predictions and see that, in fact, the predicted temperature increase for a business as usual scenario is relatively benign. What do I mean by that? We know that in Copenhagen and Paris, they said, oh, we want to make sure the temperature increase is going to be less than 2 degrees. It is going to be less than 2 degrees. Okay, so let me summarize. There are no arguments that can prove that most of the warming is anthropogenic. There are no arguments or no pieces of evidence that show you that CO2 has a large effect on climate. In fact, there are no arguments that prove the standard scenario that we hear every day in the media. And if you look more carefully, you find that the evidence points to the fact that the sun has a large effect on climate. And when you include that, when you want to try to understand the bigger picture, when you take the sun into account, you find that climate sensitivity has to be on the low side, and that is consistent with various other evidence that we have seen, for example, the low response to volcanic eruptions, the lack of correlation between CO2 and temperature over geological timescales, and so forth. So the sun has a large effect on climate, and the climate sensitivity is low. And today we know exactly how this mechanism works, how the sun affects the climate, and for that we'll hear more by Professor Svensbach in just a few seconds. So with this I'll end.